Hi everyone, my name's Dr. Vile and welcome to my YouTube channel for A-Level Chemistry. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams. And this video is going to focus on a topic called Gibbs Free Energy that falls within thermodynamics. Now you might be thinking, perhaps what is Gibbs Free Energy? It's given the term G. It's given the thermodynamic term G, and we normally refer to changes in Gibbs free energy, so we'd use the term delta G. And Gibbs free energy is all about trying to work out whether a reaction will be feasible or not. So in other words, whether a reaction will happen. And to calculate Gibbs free energy, we need to know three things. We need to know the enthalpy change of a reaction. Remember, that can either be exothermic or endothermic. So we need to know the enthalpy change. We need to know the change in entropy. I'll do a separate video on entropy. Entropy is all a measure of disorder, so whether the system is becoming more ordered or more disordered. And we also need to know the temperature as well. Now, in terms of these three terms, delta H, delta S, and delta T, delta H, when delta H is negative, that is a good thing for a reaction to be feasible. And when it is positive, that is a bad thing for the reaction being feasible. Delta S is your change in entropy, and reactions are generally more favorable when the entropy increases. So if the delta S is positive, then that is a good thing. And when delta S is negative, so the system is becoming more ordered as opposed to more disordered, that is a bad thing. And what we're going to see is how these all link together in our master equation. So the equation that you need to know for the exam is delta G equals, I want to change that G, that doesn't look very good. Delta G equals delta H minus T times delta S. Now, just a couple of things to bear in mind. Enthalpy change is normally measured in kilojoules per mole. So that's fine. T delta S, temperature is normally measured in Kelvin. And entropy, change in entropy, is usually measured in joules per mole per Kelvin. So what we have to do is divide by 1000 on the change in entropy to put it into kilojoules per mole per Kelvin. And when it comes to the calculations, we are interested in the sign of delta G. So if delta G comes out negative, that means that the reaction is feasible. And if delta G comes out positive, that means that the reaction is non-feasible. And let's have a look at some examples. So here you've got a reaction that makes boron nitride, Bn, and you're given a balanced chemical equation for it. You've then got two columns of data. You've got the enthalpy of formation of the four compounds, and then you've got the entropy in the next column. Once again, notice those units. Entropy is measured in joules per mole per Kelvin, whereas enthalpy of formation is in kilojoules per mole. The aim of the question is to calculate delta G. But before we actually get to that, we've got two things that we need to do first. We need to calculate delta H and we need to calculate delta S. Okay, so in terms of calculating delta H, if you're not sure how to do Hess cycles, it's worth watching my video on formation Hess cycles. Please note that this is a formation Hess cycle, so it's enthalpy change of formation delta HF. And when you have a formation Hess cycle, you've got reactants going to products, and then you've got the elements in their standard states down here. And because it's enthalpy of formation, you'd be forming the reactants from their elements. So the arrows would be going upwards. So if this is arrow 1, and this is arrow 2, and this is arrow 3, then arrow 1 would equal minus arrow 2, because you're going against arrow 2, plus arrow 3. Or in other words, it's 3 minus 2. Or in other words, it's products minus reactants. So we grab our calculator and we work out products minus reactants. So for the products, you've got 2 lots of boron nitride, so that's 2 times minus 254.4. I use brackets here to help me out. Plus 3 lots of water, so that's 3 lots of minus 241.8, and those are your products. And then it's minus the reactants, which is the B2O3, so that's the minus 1272.8, plus 2 lots of the ammonia, which is 2 lots of minus 46.1. And then grab your calculator, put that all in, and I get that to be 130.8 kilojoules per mole. So that means that the reaction is endothermic. In terms of calculating the entropy, delta S, the change in entropy, is basically products minus reactants. So for the products, you've got 2 lots of the boron nitride, so that's 2 times 14.8. And you've got 3 lots of water, so that's 3 times 188.7. And then minus the reactants. So that's the B2O3, which is 54, plus 2 lots of ammonia, 2 lots of 192.3. So when you put that into the calculator, you get 157.1, and that is in joules per mole per Kelvin. Remember though, to use our Gibbs Free Energy equation, we need to convert it into kilojoules. So we need to divide this by 1,000, which would be 0.1571 kilojoules per mole per Kelvin. Don't round anything really until the end. And now we're in a position where we can start plugging our numbers back into our delta G equation. So we need to remember delta G equals delta H minus T delta S, where delta H was 130.8, remember that's kilojoules per mole, then minus the temperature, which needs to be in Kelvin, so that's 298, times 0.1571, which is delta S. Remember that's kilojoules per mole per Kelvin. And that comes out as 84 plus 84 kilojoules per mole, which means at 298 Kelvin, this reaction is not feasible. Now you might wonder, at what temperature does it become feasible? Well, the point where the reaction becomes feasible is when delta G equals 0. So we could then say 0 equals delta H minus T delta S. We can rearrange this and say that T delta S equals delta H, and therefore T equals delta H over delta S. So to work out the temperature at which it becomes feasible, you plug 130.8 in, which is delta H, minus divided by 0.1571. And when you plug that into the calculator, you get 833 Kelvin, which is about 560 degrees Celsius. Okay, let's look at another example. Okay, so we've got another example here. The good news is that delta S has been done for you already, so we don't need to do the calculation for delta H. We've been given all of the enthalpy of formation data here. Okay, so we need to do a Hess cycle, and we need to calculate delta H for the reaction. Now it's formation data, therefore this is a formation Hess cycle. So if we remember how to construct a formation Hess cycle, you've got reactants going to products, and then you've got the elements down here, and the arrows must be going up. So if this is arrow 1, this is arrow 2, and this is arrow 3, then arrow 1 equals minus arrow 2 plus arrow 3, or we could say that's 3 minus 2, or we can say products minus reactants. So it's products minus reactants. So now we need to go through and do the calculation for delta H. So for the products, you've got 2 lots of this MnCl2. So that's 2 times minus 482. Plus 8 lots of water, which is minus 286. Plus 5 lots of oxygen, which is 0, so we don't need to include it. And then 2 lots of KCl, which is 2 lots of minus 436. That's our products. And then it's minus the reactants, which is 2 lots of KMNO4, which is 2 lots of minus 813. Plus 5 lots of H2O2, so that's 5 times minus 188. Plus 6 lots of the HCl, which is minus 92. And you stick all that in your calculator. And when you do, that comes out as minus 1006 kilojoules per mole. So we're now in a position where we can calculate delta G at 298 Kelvin. Delta G is equal to delta H minus T delta S, where delta H we said was minus 1006, minus the temperature, which is 298, times 9 times 10 to the minus 3, we're dividing by 1000. And that comes out as minus 1009 kilojoules per mole. So is the reaction feasible at this temperature? Yes, because delta G is negative. Let's just see one more calculation for this video, and then we'll call it quits for today. So this one has magnesium oxide reacting with carbon monoxide to form magnesium and carbon dioxide. You are told that delta H is 318 kilojoules per mole, and you've got the entropies there in your table. So firstly, let's calculate delta S. That's products minus reactants. So products, that's the magnesium, which is 32.7. And the carbon dioxide, which is 213.7. Minus the reactants, which is 26.9. And carbon monoxide, which is 197.7. And when you do that, that comes out as 21.8 joules per mole per Kelvin. So it's a positive entropy change, ever so slightly positive. And then we need to divide this by 1,000, which comes out as 0.0218 kilojoules per mole per Kelvin. Okay, so we're now in a position to calculate delta G. Remember, delta G equals delta H minus T delta S, where delta H is 318 minus the temperature, which is, I have misread the question here. It says calculate the minimum temperature at which this reaction would occur. Well, let's just see if it would occur at 298 Kelvin first. I don't think it will, based on the way the question is written, but we'll do this first and then work out the temperature at which it occurs. So it's 298 minus times by 0.0218. And when you do that, it comes out as 312 kilojoules per mole, which is very clearly not feasible. So at what temperature does it become feasible? Well, the formula I showed you on a previous question, T equals delta H over delta S. So delta H is 318 divided by delta S, which is the 0.0218. And that comes out as a very high temperature, 14,587 Kelvin. So to reduce magnesium oxide using carbon monoxide requires very high temperatures, which normally would happen in like a blast furnace. But in other words, it's not going to happen at room temperature. Watching this rather long video in the end. I hope it was helpful. If you like this video, if you found it helpful, please like, subscribe, please share with your friends, and please keep checking back for more content. Thanks everyone. See you next time.